Hey, welcome, buddy, to Calc 1 Composition Functions Introduction. I am extremely tired, but this is your host, Steve McCrae, the host and slash owner of the Great Debate Community. Well, only the owner of the Great Debate Community page and the GDC on G+, but it pisses people off when I say it, so I kind of enjoy it. We've got some background noise, and that's on my end, so let me fix that real quick. Okay. There we go. So anyways, a couple people want to do a hangout tonight. A couple people want to do different hangouts. We're doing a math one before something else tonight. This is going to be kind of a quick and dirty introduction to composite functions. One of the reasons why you kind of have to know about composite functions is that they're critical when you start learning things like the power rule, the chain rule, the quotient rule. I have presentations ready to go for the product rule and the chain rule, but I don't think we're going to get into those tonight, but we'll see. Right now, we only have like a couple viewers. So, and the other person that was actually wanting to do this didn't show tonight, which was Dragnaut. Don't know what's happening to him. He hasn't messaged me in the last 20 minutes, so I don't know what's going on. But anyways, we're going to be talking about composite functions. So let me screen share it like I usually do. And again, this is going to be a real quick and dirty kind of intro. So this is not going to teach you all you need to know about composite functions, I can assure you. And the reality is nobody likes composite functions except for EO, but he's a math dude. So, but they're not fun. Okay. Can you guys see the screen? Do I need to make it bigger? Is this big enough? Okay. As big as going to go without clipping. Okay. So what composite functions are? Think of composite functions as basically you're taking the output of one function and you're putting it to the input of another function. So think of functions as machines. You're taking something, you're sticking in a variable, which we call x, which is your independent variable. That's called your argument to the function. And you're getting a value out. That's your y, or your f of x. Or it could be a g of x, or h of x, or anything of x. But what we're basically doing is we're going to be taking the output of one of those functions and then putting it to the input of another. That's basically what a composite function is. So if you have a very simple equation, like here, y equals parenthetical group 1 plus h squared, excuse me, 1 plus x squared plus 3. I told you guys I was tired. I didn't want to do this tonight, so it's not going to be pretty. And the people that actually wanted to listen to this aren't around, so, but, oh well. So this is a composite function, and one of the reasons it's a composite function is because we can actually deconstruct it into two different variables. And what we would do is we're basically saying, look, here's the function of 1 plus x squared, okay, which is the, oh, there's Mr. Drag himself. He was having me all nervous. And I got to find out what was his issue. What was broke dick on him? Hang on. Oh, can you guys show him, please? I gave you mods. Can you guys show? Do you guys know how to show?
Not really. So we'll figure it out.
Well, you're the worst mod ever.
I told you it's my first time.
Yeah, well, I did a lot of things pretty well my first time. Giggity, giggity. Oh, whatever.
Sorry, I was in the living room.
Excuse me. Should have said you were in the bathroom. Okay, so we're talking about composite functions, and again, just real quick, a composite function is taking one function, sticking to the output of one and the input of the other. So here we have a function 1 plus x squared. Now that output, right, wherever that output is, we're going to put in the cubing function. So when you see something like x cubed, that literally is a function. That's a cubing function. X squared is a squaring function. So we can actually break this down, and this is something you have to get really, really good at in calculus.
If you don't master this, you will fuck up later. I guarantee you. Yeah, I speak from personal experience.
No matter how you know what, Drag? No matter how good you think you get this down, you still fuck it up.
Oh yeah, especially when you get to fucking right. What do you do right before you get to integrations?
Substitute by part, integration by parts.
You have to use it as a fucking sigma, I think, or it's something else. Anyway, we'll get to it. Anyway, I forgot what it was.
Okay, well, okay, so yeah, so some of the summations, but okay, so listen what we're actually doing here. We're gonna actually deconstruct this particular equation here. So we can actually say that if I just want to say y equals u cubed, in other words, u is going to be the function 1 plus x squared. Okay, so you have to take it as you could. I prefer to go into out, but he'll probably say you have to go out from in. I don't care. Whatever works for you.
I go inward.
What do you do?
Yeah, the same thing as you should
you
go
in,
from in.
You go into out.
Yeah.
Okay.
I agree.
Okay, cool. Because I find that to be a lot easier. So the way I would start looking at this, okay, what is my parenthetical group? That is my one function. So that is 1 plus x squared. I'm going to assign that to the variable u. Okay. And then that output, I want to have into the cubing functions. Okay. So y is now equal to u cubed, where u equals the parenthetical group there. So I now substituted it into two different variables. I've deconstructed it to two different variables. So here y equals u cubed, where u equals 1 plus x cubed. Now, one thing to remember is that if f and g are functions, again, we really didn't go too much over functions and relationships, but basically a function has a one-to-one correspondence with an input to an output. And I'm going to get into that a little bit more as we progress. But if you suppose that x of g of x is in the domain of x, domain of f, what that means is if the g of x can be put into the domain of f, it can be put in the input. Think of it, domain as the input, range as the output, right? So domain is all the values of x that you can have where you can get an actual real y value out. And we didn't go over domain and range. That's a whole different topic. But you can think about it just real simply as for a domain, it's any value for x where you can get a real value of y out of. You want to avoid things like division by 0, so you don't want to have a denominator with 0 in it. You want to avoid things like negative numbers underneath the radical, right? Because that's going to be a problem. Well, we're going to get into that a little bit. I do want to show you a little about domain and range because you're going to have to know a little bit about it. But basically, this is just saying that g of x, you can put the output of that into the input of f, okay? So, and we'll get into the fact that actually on some of the inverse functions that the range is actually equal to the domain of the other, and the domain is equal to the range of the other. But we'll get that. We'll get there eventually. So, all right. So the way you actually note this, okay, this is actually read the composite function is given by f g of x, right? Or denoted by f circle g. Okay, so that little, can you guys see that little circle, or is it too small?
We can see it.
I just want to make sure. So, I know it's going to clip too much. Okay, there we go. So that little circle sign, it means a composite. It doesn't mean times. It doesn't mean things like geometry. It just means that it's going to be a composite function. Do we know this person, Lapinu FR6? I don't know him.
Think of the domain as a set of all possible inputs, and we always read this as f of g of x. And Steve makes a good point. The circle means composition. If there is no sign, just like multiplication, we mean multiplication, or if we put a star, we mean multiplication. And please be aware, composition is a very different operation than multiplication.
Yeah, multiplication, if they use dot, it's actually going to be blackened in. But I don't like dot because in some types of math, you'll discover that dot's actually used as something else. It means a dot product. So if you get into vectors, you don't want to use dot because it doesn't mean the same thing. But I don't know the people in the live chat asking for links, so I can't do it. So anyway, so this is what it means. So if I have f of a function of f of g of x, so f is a composite of g. You could break that down. You're going to assign the variables g of x equals u and f of u equals y. Then f composite g of x equals y. Now that looks kind of complicated, but we're going to break it down a little further because it's not as bad as it really looks. Basically, what it's saying is, let's take the if you have the composite f of g, right? You're going to take one value that you're going to take the g of x, and then you're going to stick it in the function for f of x. Basically, all you're doing is getting the value for one function and you're putting into the next. But you'll find that in some functions, f of g is different than g of f. Okay, not all functions are like that. Some will be different. Some will be the same. So we're going to get into that as well. So this is going to be the composite of two functions. And by the way, did you ever find out if Ronnie wanted to join us? I'll be happy. He can sit and just listen. I don't care.
He was in my live chat, but I don't see him in this one. I let him know. I said it a few times.
All right. So something like this. This is a composite of two functions, or more. It should be actually two or more functions. It's actually three. More, say, composite of more than two functions. So, Drag, if you look in here, can you kind of visualize how many functions you think are going on here?
Oh fuck! There has to be at least 3. I want to say.
Okay, so let's start from the inside, because again, I like going in and out. That's not dirtier than it sounded. Not a single laugh. Wow, you guys. I'm tired.
This is math. This is serious.
Yeah, this is serious stuff. Okay. So the first function, y plus y plus x squared, right? That's a parenthetical group. It's got the parentheses, so that's going to be one function, right? We're going to assign that to be v. So these, I know he's going to get me on this one, but these are somewhat arbitrary. We tend to use the higher numbers for variables and the lower, the higher letters for variables and the lower letters for more constants, right? A, B, C are more like the coefficients of things, and then U, V, Y, those things are usually more variables. But there is a reason why we use the U and V here, because there is notations using this specific type of UV notation, which again we'll get into. So if that first function, right, 1 plus x squared is v, you're going to put that into the next function. What's the next function?
Oh, shit.
Once you get that number, what do you raise it to?
I'll raise it to the 5th power, so that's to be that v to the 5th.
That's v to the 5th. So v is that 1 plus x squared, right? You stick it into the 5th function, 5ing function, right? You raise it to the 5 power, right? But then you've got that going into another function. What's the very last function it's doing?
Then it's all under square root.
That's a square root function, right? So what you're doing is you're taking the output from 1x squared, you're putting it into raising it to the 5th power, then you're taking the square root of that. So there's 3 functions going on. Each one's assigned a different variable. And one of the reasons to do this is not just so you can actually take derivatives and products and all that other stuff. It's a lot easier to write one letter than it is a whole long formula. I mean, instead of having to write 1 plus x squared out every time, you just write v, right? Because you know what it's assigned to because you've assigned it to it, correct? Oh, Jade wants the link. You can get me that.
All right.
I totally forgot. I'm sorry, Jade.
Okay. I got her.
Drag asked me to give you a couple of practical examples why we even need to study this. So the first thing is what composition allows you to do is to take basic functions and create more and more functions. You can create infinitely many functions by composing one with the other. So here's a very simple example. He asked, suppose, Drag, you wanted to calculate your taxes for a given year. So you would take your salary and you have a formula for your salary, but then you'd have to take the tax formulas and the input would be your salary and the tax formulas would operate on that. So there's an example. In physics, in Steve's domain, I mean, this comes up all the time. You have square roots of squares. So the point is the composition of functions is a way that we can combine 2 or 3 or 4 or 5, or you can see sometimes 6 or 7 comes up in practical applications all the time.
Yeah, you also use them in time rate of change problems with salinity, and when you're doing concentrations of, let's say you got a vat that's a certain amount of salinity level, and you've got a pipe going in and a pipe coming out, and they're different sizes, and one's a different height, and you got to use a Bernoulli equation and composite functions and differentials, and you got to figure out, okay, after 5 hours, how much is my concentration of the solution, kind of thing, which you never ever do in real life, but you got to do it for school, right? Because they love teaching you things you never do in real life.
Didn't King Crocoduck have a similar type of thing with the liquids in one of his videos? I don't know if that's
probably, yeah. That's one thing. I mean, one of the basic things people learn is called mixing rates, and mixing rates have to do with solutions and how much concentration you have in that particular solution. But can we show Jade? She looks lonely.
Hey, Jade.
I don't have mods, so I can't show anybody.
EO does. EO, do you know how to show her? Just go the little arrow. There you go. All right. So that's how you do a composite of more than 2 functions. And by the way, this is the easy stuff. It gets worse, guys. It gets worse. Trust me. Okay. So I'm not like your regular math guy. I don't tell you how, it's so easy stuff. No, I tell you it's shit. Okay. So given something simple like this, let's say I have the function x equals 2 raised to the x to the 2nd. Something like this. Again, we already did our order of operations hangout, right? So we know we always do exponents first. Here we have a parenthetical group of the exponent. which means that we would normally take the exponent of the x first and then 2 to that. So we could actually break it down and say, okay, what is my exponent there? Well, the exponent is x squared. Well, I can assign that to be a variable, right? And I'll attribute it to u. So I say u equals x squared, right? And so then what do I do though? Where do I got to put that? Because it's still another function, right? It's an exponential function, right? So that u is going to be in the place of x squared. So y is going to be equal to 2u, where u stands for x squared. You can see this one pretty easily, right? This one's pretty easy to visualize, correct?
Yeah.
Y equals 2 to u, and u just stands for x squared, right? Then you just substitute in. Those are pretty easy. Now, here's where some of the differences come in. When you want to figure out a composite function of f of g compared to g of x, this is how they can differ or they can be the same, depending on the function. So let's say I have two functions here. I have f of x, 1 plus 2x, and g of x equals x squared. If I want to compute the f of g, and I want to compute the g of f and compare them, this is how I would do it. So my very first step is f of g of x, right, is equal to f g of x. And this goes back to my very first definition here. It's just right here. It's very, very simple definition. It's just composite. So I'm just putting it as a composite. Now, g of x, right, this right here, remember, this is the argument to this function, right? So this argument is actually this right here, because this is what it's equal to. So I'm going to take x squared, and I'm going to put it right into this argument here. This gives me f x squared, correct? Now this f of x squared, this x squared is the argument to here, right? So I'm actually here. So I'm plugging it into this x here. So now I end up with 1 plus 2 x squared. This right here is my composite. Okay, so basically what I did was, again, I took this equation, this function here, I stuck it in for this argument, giving me f x squared, and then I took the output of that, which is x squared, into the input of here. Give me 1, 2 x squared. Does that make sense? We good?
We good?
Okay, so
it's like you took multiple parts of something and put it together to make a whole.
yeah, well, yeah, you're sticking two functions together and you're making one out of it. Yeah. So let's look if it's the same thing as the reverse. So let's composite it the other way. Okay, so here I broke it down. I have g of f of x, g f of x. Again, this is what they're defined to be. This is saying that f of x is the argument to g. So f of x is what? 1 plus 2x. Okay, let's stick that in here. So I have g 1 plus 2x. Now, the g function is this. It's a squaring function. So if this is a squaring function, what do you think this should look like? Before I show it. If this right here is going to be going into this x, what's that going to look like?
Yeah, the whole thing's going to be squared.
The whole thing's going to be squared. There you go. So it's 1 plus 2x squared, because I'm just taking this and I'm putting it in here. So the first way here, I put it here to here, and the bottom way I put them here to here. Now, are these the same equation?
I think I can't see anything your mouse pointer. I can't see, like, when you're saying here and here. Yeah, like when you're saying here and here, I was like, I'm.
Who can't see my mouse pointer?
I can see it.
Is 1 plus 2x squared the same as parenthetical group 1 plus 2x squared?
No, of course it's not.
No,
that's not.
No, that's two different ones.
Two different ones. I mean, with the bottom one, you would have to do a binomial distribution. Again, one of the reasons why we went over binomial distribution.
Squared.
As we've learned, math, you continue building things from prior things, right? Because we would have been screwed if we hadn't gone over half the stuff we did before we even started getting into calc, right? So these are not the same function. So this one, actually, the composite is different. The f of g of x is different from g composite f. Okay, so in this example, they're not the same because go ahead.
Not a commutative operation, and that's what Steve just showed. And it's important to remember, in logic and in math, a single counterexample disproves a rule. So Steve just demonstrated that composition of operation for all those who
It's not
like
commutative.
logic pretty simple.
Yeah, because if I can find one exception, it's done, right? But you just need one. So this is a single case where it just shows that f of g is not always the same as g of x. It could be, though. It could be, but this is one example that it's not. So let's do something really simple. Let's actually have the function of a function that's the same function. Okay? So this is a composite function where you're just taking the output of the function, you put it into the output of the same function. So if I have f of x equals negative x, right? And I want to know f composite f of x, then I just put it in this formula, in this format, right? It's just a function f of x with the argument f of x, right? You guys have kind of figured out how to make this argument work, right? If this was a g here, it'd be g f of x. If it was a g here, it'd be f g of x. So you're just putting in, you're just taking this and putting it as an argument to the input to the next function. So if f of x is equal to negative x, I just stick in negative x, right? Right? Since f of x equals negative x, I just put negative x in for this argument. Boom. Well, now I have to put it into f of x. Now I have to put it into the same function. So if I put negative x into the same function, right here, negative x, I get negative x. And what happens when you have negative with a negative?
Turns positive.
Turns positive, right? Negative times negative is positive. So this will give me x. So f composite f, or f of x equals x. Now, what kind of function do you think it would be when it takes a negative and makes it positive?
Inverse.
Inversing function. Wait, is this an inversing? Let me think here.
I'm guessing. I'm not sure.
You found the inverse.
Well, no, but it's not. It's not inverse, is it? Yeah, we're gonna get okay. Yeah, we're gonna jump down. I'll show you because I remember I did do inverses for this, so I'll show you actually what an inverse function actually is.
To even talk about an inverse, you have to define the identity element first, too. That's kind of
the identity element for, well, there's the identity element. There's multiple. Okay, if you want to know the identity elements, well, I don't know. We never got into this stuff, but there's a multiplicative identity. Anybody want? Don't say it, Dio. What do you guys want to guess what the multiplicative identity is? What number?
One.
Okay. What is the additive?
Zero.
Okay, so those are two types of identities. Very good. How'd you guys know that? Oh, you're smart.
Duh.
Well, I was expecting Ronnie in here. Okay, so hello.
ATP synthase beak.
ATP synthase is the right answer to everything. From here on out, every answer is ATP synthase. Okay, so the multiplicative identity of ATP mainase is beak.
Yes.
Okay, so I wanted to show you guys this notation. This is kind of out beyond the scope, but you will be introduced to it at some point. This is more of a mapping type notation, and even though mapping and functions are used kind of interchangeably, there's some technical differences. Maybe you might be able to explain the nuances between them, but this is basically saying you're taking a function of the reals and your output is going to be a real. Okay, so it maps from the reals to the reals. It doesn't have to, though, right? Things can map to the complex, can map to the reals. You can map from x to y, whatever your sets are. So this is the set of all real numbers. The function is mapping from a one-to-one correspondence with the set of all r. And this means that there's a relationship from the reals to the reals with a property that every element A of R, there's exactly one element B as an element of R. All that basically means is that for every single input you put in, you can only get one input out. There can never be two outputs for one input. We good on that? Not for a function, at least. Right?
So far, so good.
Is that good? All right.
That's good, but hang on, Steve. You can't talk about inverses without defining the identity element first. That's you're putting the cart before the horse. There's no debate, Steve. You can't do that. You have to define f of x equals x as the identity element. Otherwise, inverses don't even make sense.
Well, okay. Well, are you talking about f raised to the -1?
No. But just so we know, if you want to talk about That's fine. Go ahead. So I go to inverse functions. But if you're going to do composition, you have to mention, okay, for every composition, every single composition, if you compose it with the function y equals x, you'll always get in what you put out. So it's your identity for composition. Then from there, you can talk about what it means to have an inverse function.
What?
If for every, okay, run that slowly again.
Do you see the example you just chose of f of x equals minus x, and you composed it with itself?
Yeah,
Do you
yeah.
see that?
Yeah.
Okay. So what you was that f was its own inverse because you ended up with the identity element. In the same way, for example, that 3 times 1 over 3 equals 1, reciprocal inverse of 3, because when you multiply by each other, you get the multiplicative identity.
Okay,
So,
yeah, you know what? I kind of get on that when I hit odd and even functions. That's when you'll get really into the multiplicative identity, because obviously with squaring functions, it's going to be different than the like an odd function. But all right, so let's see if we can work through it and then jump in when you think you want to add that. Okay, so an inverse function, basically, if it's mapping from one set to another set, the inverse is going to map the other way around. So all the values in the domain of f minus 1, which is the inverse function of f. Okay, so I'll give you an example. If the function is x squared, right? If that's the function, what do you think the inverse function of x squared is?
1 over
Square root.
Square root.
Square root.
Right, because they cancel each other out, right? They're the inverse. They do the opposite function. One squares it, and the other one takes the square root. So basically, they negate each other, right? So the values of the domain of this inverse are actually the range of the values of the function, and then the range of the values of the inverse are the main values of the function. So basically, again, the domains of the input, the range of the output, and basically this is just saying that the input of the inverse function are now the range values of the function, and then the other way around. And I did actually go further, and I'll give you an example of a domain and range because we didn't talk about it, and you may not remember it. So I think it's kind of behooving us to at least give an example. Would that make sense? Would that be a good idea, Yo?
a major foundation which we've left out is the fact that whenever you talk about composition functions, the domain is a serious problem. For example, you could have the logarithm of my problem. So there's a rule that I used to teach my students. The domain of the composition is the domain of the inner function, intersected with the domain of the composition. But that's probably too far afield. But yeah, I just want to tell the audience there's a major foundation of composition of functions, namely, you have to intersect your domains. You have to check to make sure. I mean, here's a good example. The logarithm of x, the domain is only the positive real numbers. But if I took the logarithm of x squared plus 1, then your domain gets changed to all real numbers. So there's a slight.
You have to know what the domain and range.
Yeah.
I have an example of that very thing. I don't use logarithms, but I could have. But I'm going to give an example of that. So hang on. Okay, so the domain is all the allowable x values to the input. Range are all possible real x, real y outputs, basically. And again, we don't want to have anything like 0 in the denominator, because that's not. You can't take the derivative, obviously, if you have 0 in the denominator, because what kind of line does that produce? Anybody remember? What kind of line is not differentiable?
Undefinable line?
Well, yeah. Which type? What is that? A horizontal or vertical?
Oh, that's a vertical.
Vertical. Right. So if it's vertical, then it's undefined. So we can't take the derivative if it's undefined. And so when you're taking the domain, you've got to know if the values of x are appropriate, right? If I have, and I'm just throwing this example, I didn't write this down, but if I have like the reciprocal function of x, right, 1 over x, 0 is not in the domain of that, right? Because 0 would give that 1 over 0, which is undefined. So 0 is not in the domain of that, but any other real number, it works. Right? So that's what we mean by domain. So when final domain is the fraction cannot be 0, and the number under the square root sign must be positive. And let me show you what I mean by that. And I actually did this on the graphing program. So if I wanted to find the domain of the range of something like this, square root of x minus 4. The domain are all values of x that produce a real y. Therefore, x has to be greater than or equal to 4. If I put 4 in here, I get 4 minus 4. I get 0. Square root of 0 is 0. I have a y output. Y is a real number, right? If I put 5 in there, 5 minus 4 is 1. Square root of 1, 1. Y is a real number. If I put a negative higher than 4 in there, right? If I put a value less than 4, I put let's say put 0 in there, x equals 0. Well, let's see. No, let's see. 0 minus 4. Yeah. So what's the square root of negative 4?
2i.
Well, 2.
Yes. I thought it was 2. So I thought it was an imaginary number since it's negative.
Yeah. It's going to be 2i, right? Is it 2i or negative 2i? It's 2i.
It's
right?
2i. No, yeah, there's no square root.
Okay, so it's 2i because the square root of negative 1 is I. So it's an imaginary number, right? So it's not going to be a real number. So you can't have the domain in there where you are getting an imaginary number in the complex plane, which, by the way, we have not gone over yet, which we will eventually, because complex numbers are kind of fun, actually, in a way. But we haven't touched the complex. If we're doing a complex, just real quick, see this fancy-looking R? It's called a bold double strike. That'll be a C if you're dealing with a complex. Just throw that out there. So,
okay.
To clarify for everybody, this is plus or minus 2i in the same way the square root of 4 is plus or minus 2.
Fair enough. Yeah, I guess you're right.
Review
Plus or
that
minus
next
2i.
time.
Yeah, that's a good. You know what? When we start doing complex stuff, I'll have to review a lot on complex and imaginary numbers. But I will tell you this: I actually been into arguments on this, and I've won every time. And I know Ian knows I'm right. The reals are a subset of the complex numbers.
Yes.
So a lot of people have a hard time understanding why that is.
Right, Steve, but you have to be careful. The reals are a subset of complex numbers, but not all cars are Ferraris, so you can't call. So you can't call a complex number a real number.
No. That's the other way around. You don't want to do that, right? But all reals are complex, but not all complex are reals. But the reason being is that every complex number, if you remember, now we're going off topic, but every complex number every complex number consists of a real part and an imaginary part, right? In the form of a plus bi. If it's in the form of a plus bi, and b equals 0, right? What do you have?
A real.
Right. So you just have the real portion of that. So, and by the way, Midnight's doing a presentation on this at some point because he asked this kind of similar question and I didn't answer him for a reason. I actually said, you know what? Go look this one up because I think it'll be more beneficial if you kind of look at it yourself. And he did, and he got it straight up right. So kudos to him, man. Awesome. Okay, so range are all possible values for y. So if I actually show you this,
Kaiser needs to be presented.
if I actually show you this, what this looks like on a graph, okay, ba-boom. This is that square root of x plus 4. Now you notice it starts at negative 4, right? Which now remember, if you really think about it, the domain is pretty much your x-axis, right? Any number we can put in for the x-axis, and then if the domain is the x-axis, what do you think the range is? The y-axis. Okay.
Steve, I'm so sorry. That's not the graph. This is y equals the square root of x plus 4. What you wrote was the square root of x minus
right.
4.
Yeah, but they look exact here. You're right. There you go. It's just on the other side. You're right. Sorry about that.
That's good.
Yeah. All right. So they look exactly like. You can just see the way they moved. I was actually trying something. So what this is actually saying is that, again, remember the domain? We said 4 equal to or greater than 4. So here this is right. So x has to be 4 or greater than. We can see visually that obviously the only things that work on here is 4 or greater. Now the range is anything greater than what? What's the output going to be? All the outputs are here are equal to something and greater. What? 0, right? So that's what we meant by the range is 0 to infinity.
So Steve, let me take over here for a second. This is really important. Can you go back to that graph?
I'm on the graph.
Yeah. So this is important. Some of you might be wondering, well, I learned in school that the square root of 9 has 2 square roots, plus or minus 3.
Oh, we'll get into that. We'll get into that.
No, but
I'll get into that. Yeah,
so there's a reason why we only consider one of the square roots. If you were to draw the other branch of this, it would no longer be a function; it would be a relation. That's why we only consider the principal square root. Can everyone see that?
Yeah. When we take the principal square root, right, the squaring function or the square root function takes the positive always the positive, which is called the primary square root. And for that very reason, if you took the negative, your function is now turned into relation, and now you have two outputs for one input. Not good, because then you're no longer dealing with functions, right? One thing that, and I will get into this, because there's one of the big problems that you will have if you just start off in algebra and stuff like that, is if I just tell somebody something like, you know, what is the square of -3? It's ambiguous as stated, and I'll show you why. And when you see it written, there's a specific way to do that, and I'll go into that, because if not, you're going to get the wrong answer. But I got that coming up, so let's bear that in mind. But let's go on with the functions, and now I'm going to show you what I mean by the square root, why it's important to actually know what you're actually squaring, right? Because you got to remember that minus is a unitary operator. It's not a binary operator, and I'll show you what I mean by that too, if you don't know. So if I have f of x, right, is a cubing function, right, x cubed, and g of x is the cube root function. Now, we already know that that's the inverse function, right? We've already realized that. But let's see what happens when we actually compute f of x as opposed to g of x. And I lost my live feed there. One sec. Okay. So we're going to start off with the first composite, f composite g of x. And again, I'm just sticking in the g of x is the argument of f, right? G of x, the argument of f. What is g of x here? The cube root of x.
Cube root, sorry.
Okay, so I'm putting the cube of x here, right? And then I'm taking the cube root of x, and when I'm sticking into what other function? I'm taking this cube root of x, and I got to put it somewhere, and I'm putting it to the input of the other function. What is the other function's input? No, x cubed, right? This x up here is my next function. So I'm taking this function, and can you see my mouse? I'm taking the cube root function, I'm sticking it into x cubed function. So I'm just putting it in there, and I end up with, instead of having x cubed, I end up with cube root x cubed. And what happens when you take the cube root of a exponential of 3, or vice versa? What happens to them?
They cancel out.
They cancel out, right? They're inverse, right? No worries. No worries. Okay, so here it just returns the value of x, right? Is the inverse function. Okay.
Right. So this was the point I was making earlier, Steve. You can see that when you compose f with g or g with f, you get the same result, namely x, and x is the identity element. So what Steve has shown then is that these two functions are inverses of each other precisely because their composition is the identity element, namely f of x equals x.
Yeah, exactly. See, because I composite it either way, I can take f of x, x composite g, or g composite of f, or however you want to say it. You can say f composite g or f of g, but they'll give you the exact same original variable, right? They'll basically return the same variable either way, and that means you can put one to the other one, or the other one to the first one. It doesn't matter, because you're gonna get the same value, which is the variable x. These are inverse functions. So if I take the composite g of f, it's the same thing. I'm just taking f of x, which is x cubed, right? Sticking it in here. So now I take x cubed when I'm taking the g of x of it, right? Now my function is g. Well, what is my g function? My g function is the cube root of that, right? So what happens when I take the cube root of x cubed? Again, they go away. I'm left with x. Now you're generally going to see inverse functions expressed as this notation, okay? F raised to the -1, okay? This is not f raised to the negative exponent, okay? When you see a negative on the exponent, it generally means an inverse. Like, for example, if I have x to the -1, right? X to the -1 is what? Well, it's 1 over x, right? Yeah, it's 1 over x. Yeah, well, you know what? Same thing though, right? If I have, and I hate trig, but God, it has been a while since I did my trig. But if I have something like sine, right? The inverse sine, which would be the what? Cosecant? Secant? Oh yeah, so okay. This is where I always screw up. Sine, the inverse of sine is secant. And
No,
the inverse
guys,
is cosine.
no, stop.
Or the other way around.
No, all of you are butchering it. No. You're confusing.
This is why I hate trig.
No, guys, everyone calm down. You're confusing reciprocal trigonometric functions with inverse trigonometric functions.
Yeah.
So 1 over sine is
1 over sine,
but arc sine is the inverse of sine.
Arc
so
sine.
please be careful.
Okay. Yeah. So yeah, it's a lot easier when you're seeing it in your head. I haven't looked at 7 ages. So if I have 1 over sine,
right, that's cosecant. But if I may, Steve.
Yeah.
So what the excellent point you were making is that f inverse, as written, means the inverse function of f if suitably restricted. However, 1 over f means the reciprocal of f, and those are two different things. So
two things, right? So don't confuse the nomenclature, because you will be getting into that, especially like when you start doing the tan -1 and sine -1 and all that other happy horse.
And Steve, let me apologize for my tone. I was a teacher, and I will be again, and I just want to make sure no one goes down that path of confusing the two.
Oh yeah, no, and it's easy to do though, right? It's really easy to make those mistakes, especially when I haven't looked at it in ages. But I when it comes to trig, I'm much better if I just look at it, right? I hate doing that stuff. Oh yeah, I should know. All right, so moving on here. So if f of x is equal to x cubed, right? Then what's the inverse function? What's the inverse function of x cubed? Third root of x, right? So
Steve, if I can indulge the panel.
Yep.
If f of x equals x to any odd power, can all of you tell me what the inverse must be? So, for example, f of x equals x to the 91st. Drag, you still there?
Square.
90, yeah, I'm here. So it'd be the 91st root of that.
Yes.
Yeah.
Yes.
So any root is going to be it's going to be the root. So if I for example, when that little radical sign, okay, let me explain this real quick. This radical sign here, this little bar again is called a vinculum. It means anything under this, that's what you take the root of, and this third means you take the nth root, which is the third nth root. Okay, and if you say for any inverse function, if I pick x to the 5th, the inverse function is going to be the 5th root of x, right? And vice versa. If I say what's the inverse function of the 5th root of x, it's just x to the 5th. Does it make sense?
Yeah. And it's also x to the power of 1/5.
Yes, you can write them in fractional notation, which, by the way, I pretty much wanted to do a presentation on. You don't see fractional notations often, but when you do, they tend to confuse people a lot because it's just not what people are used to seeing.
It depends on what you learn first.
Well, and also when you're using fractional exponents, you can make some really easy mistakes really quickly and end up some really screwy results in your proof.
It depends, Steve, where you learn it. Like I said, because sometimes, for example, if you're raising x to the 1/2 to the 2/3, using fractional exponents makes a lot more sense than using radicals.
That's true.
Can I make just a subtle point here?
Yeah.
I'm really glad the panel. You might notice, everyone, that I specified odd powers. Everyone notice that x to the 91, x to the 5th?
Yeah, because it doesn't work for even powers.
Well, and the reason is it has to do with the fact that the odd powers are 1 to 1. I don't know whether Steve wants to get into restriction of domains for inverses.
No, not yet.
So go ahead with even functions. And by the way, even functions are really important, odd functions, because they make integration easier, and they're neat properties to have. Go ahead, Steve.
Yeah, I'm gonna explain those too, but I want Rob Hartward put something very, very good in the live chat. He says the word inverse has different meanings, which is very true. The multiplicative inverse, which is going to be 1 over x, right? 1 divided by x. But the inverse function here is not the same. The inverse function here is not 1 over x. It is the function that undoes another function. If you want to think about it that way, that's how I learned it. It undoes the function. So if f does this, then the inverse undoes that function. Does that work?
No, and that's exactly right.
That's how I learned it. So
no, it's exactly right. And the point is, he's right about context, but we should be careful. It's clear from the context we were talking about composition of functions. And so when we said the inverse, that was clear. For example, if we go to the dentist office and he talks about calculus, he means the plaque on our teeth. Just so we're clear, like context is everything.
That's true. That's true. But I mean,
yes.
but it is something that it should be noted that some of these words do mean different things in different in context in math. So you got to know what kind of math you're looking at sometimes. So, all right. So moving on, let's talk about even and odd functions. So here, let me give you an example of an even function. Now, obviously, an even function is in any value where n, something raised to the n, is an even number, right? 2, 4, 6, 8. Those are all even functions. So let's start off. If I have f of x, x to the fourth, okay, excuse me, and I put in negative x there, right? So negative x is now my argument. This is how this reads, by the way. This reads as the negative x argument that'll go into this particular function. Remember, we're just sticking one argument for the input to the other. So if I have minus x as x here, right, what do I end up with? I end up with negative x to the fourth, right? And if you take an even number, if you take a negative x and you take an even number of it, it always makes it positive, right? So if I have, negative x squared, it makes a positive, correct? If I have negative x fourth, it makes a positive. Doesn't work for odd, but for even, that's what it does, right? We good? Because even a -1, right? -1 times -1 is 1, but if you do it another time, you do it 3 times, or you take it back to the third, you end up with -1 again, right? So any even will give you a positive result. And here we have x to the fourth equals f of x. So basically, this is an even function. So the way you write this is for all even functions. Anybody know what IFF means? I'm throwing these terms in here. Again, I got these from multiple different places. I've got like 6 different sources, my calculus book here, and and I throw these things together to give you a little bit of taste of everything. What does IFF means?
If and only if.
If and only if.
So biconditional.
Yeah, it's biconditional. So that this means that it only be the case if this is to be true, and only if this is to be true. Okay.
So So Jade is in the chat. I know. So Jade knows a lot about logic. So if IFF is simply A implies B and B implies A. Everyone got that?
Yeah. Biconditional meaning that if A implies B, then B implies A. There's a directional. In logic, it'd be a double. It looks like a double-headed arrow, meaning biconditionality. Okay. Which, by the way, I wouldn't mind hanging on logic either. I'm getting better at logic, thanks to like Dr. Alex Malpass and those guys are like forcing it upon people. So anyways, here I have the argument negative x equals f of x. We already determined that up here, right? In the even function. For an even function, I put in a negative value. I put in negative x, and what do I get out of it? I got x. So if I put in -2, what do I get out of it? I'll get -2 to the fourth. What's 2, 4, 8, 16? All right. So it always give me a positive number, right? So the negative x will always be equal to the argument of x. It won't matter if I put an x or I put in a negative x, I'll get a positive value out of it. So if it doesn't matter if I put in -2 or 2, I'll get the same value. So of all of x in the domain of f, okay? Again, x has to be in the domain of these things. If x is somehow, if it's a 1 over x, it doesn't work, right? Because if you have like 0, it's not in the domain of f. Now here's what's really kind of cool. And this is something you're really gonna have to memorize, because when you do pre-calc or college algebra, you do a lot of graphing. So it's really helpful to know by just looking at a graph if it's an even or odd function. And an even function, and I've got one here, right here, boom, let me get it to you. Let me get rid of the other one. An even function is always going to be symmetrical of the y-axis. Okay, here's my y-axis going straight down the middle there. Everything on this side is mirrored on the other side. It's symmetry here. There's a symmetry from this side to this side. Everybody can see that? So it's flipped from the x-axis. On any even function, I could raise this to any power I want. That's even. 2, look at that. If I do odd 6, if I do 9, 8. That's those are odd. So any even function, right? And if you notice, if the bottom starts getting flattened out, right? So as I go up here, so if I have like 100, that's more of a graphing problem, but because
right. So you have to change the scale. So if I may, Steve,
I got to change the scale. Yeah.
So everyone, if xy is a point on the graph, then minus x comma y is also a point on the graph for even functions. As Steve said, even functions are symmetric about the y-axis. A really important even function is cosine. All right, everybody? So cosine of minus x equals cosine of x.
Yeah, and at some point, I could do cosine and sine functions and do the domain and range and all that kind of stuff. At some point, that'll probably be an interesting discussion, actually. But let me show you guys this too. If I did that, okay, what is it? What did I actually do? I added a negative sign, and what happened? It was inverse of the other function, right? Pretty cool. But that's beside the point. But
don't throw around the term inverse here.
Well, it kind of is. It's actually what's called a oh, hang on. It's called a
negative reflect. It's a reflection about the y-axis.
Negative reflection symmetry.
Yeah.
No, it's still an even function.
It's still an even function. Yeah, it's still an even function. But I'll show you where it's critical to actually get the argument right. But let me get into that in a second. Okay, so just bear with me for a second here. Let's do an odd function first. An odd function, right? X cubed would be an odd function because the exponent's odd. So let's see what happens when I put a negative x in there, right? Negative x is the argument. So where again does this, shout it out, where does this negative x go? What do I do with it? I put it where?
Into the function, into the place of the x.
In place of the x. So this goes in here. Now I have negative x to the third, right? Which is actually equal, and this is only equal for an odd function here. This is where I would screw up rarely. Remember Drag? Is Drag still in here? Drag's not even here anymore, is he? Guys? Is Drag not in here? Oh, okay. Whoa. Okay, so I always said when I was in nuke school and calculus and stuff, negative signs were my bane. Okay, and I wish I would have gotten this down because I screwed up always having negative signs. But here this is an odd function. You can actually draw the negative sign out. Okay, and you end up with negative f of x. So the argument of negative x for the function of f will actually be equal to negative f of x. You can't do that for an even function. And let me show you. I think I wrote this down here somewhere. Did I write it? I'm pretty sure I did, but no, damn it, I didn't.
If I may help with the geometric interpretation.
Yeah.
Everyone, for odd functions, they're symmetric with respect to the origin. What that means is if x, y is a point in the graph, minus x minus y is also a point. And what that means in practical terms is if you take your graph, flip it about the y-axis and then the x-axis, you get the same graph you started with. Does that make sense to everybody?
This right here. See, if you notice here, what he's saying is an odd function will always be reflective on the origin. Where's the origin? 0, 0, right? So see how the graph approaches here and then it does the same thing on the way out? That's an odd function. So every function that's odd is going to look like that. So let's try 7. See? Okay, so it's reflective on the origin. Now, let me ask you something. If I have something like this, don't answer, EO. If I have an odd function.
Sorry, Steve, it's symmetric with respect to the origin, not reflective.
Okay, it's symmetric with respect to the origin. You're right. So here I have it symmetrical with respect to y equals 2. Don't say anything, EO. Is this an odd function?
No.
No, because remember, all odd functions are symmetrical with respect only to the origin. Okay, only to the origin. So that would be neither odd nor even. It's only when the origin here is reflected at this point 0, 0 as an odd function. Very critical to know. Very critical to know. So even functions are symmetrical from the y-axis, and odd functions are symmetrical from the origin.
Steve, can you go back to the graph?
So a sine is an odd function.
Okay, go back to what?
Sine is an odd function, Barney, yes. Could you go back to the graph for a second? Okay, so really quickly, can everybody see that the area above the curve, if you start at 0, is always equivalent to the area below the curve, depending how far you go left, right? Can all of you see that?
What? No.
So all this area here is equal. All the area above here is equal to the area below here.
Okay.
That makes it very convenient for integration. And if you go back to the even function, the area to the right of 0 equals the area to the left of 0, which means that your integral, you only have to integrate once. It makes, like I said, even odd functions come up a lot, and it makes integration easier in certain cases, and it's an important thing to know. Go ahead, Steve.
Yeah, because this area from the y-axis to the function, the area here, the integral is going to be the same as the integral here. They're going to be equal. Okay, so that's getting into integration, but we're a whole different topic. But anyways, let me explain this. This is good. If you ever learn anything from anything that I've said ever, memorize this till the day you die, what I'm about to tell you, because I guarantee it, you will mess it up at some point, because I did. So minus is a unary operator. A unary operator means it attaches, it only operates on one thing. A binary operator means two. You have two inputs to it. You have like 5 times 5, right? The multiplication is a binary operator. It requires 2 things, 5 and 5. But a unary operator does not. It requires 1. If I say -2 squared, okay, you do not take the -2 and square it. You always do the order of operations, which is exponentiation first, right? So, and I guarantee it, you will find people that will tell you this is wrong. Tell them to go to EO, and EO will beat them silly. If you have negative, and I'm not lying, I had an engineer tell me this was wrong. And I'm like, dude, you're full of it. -2 squared. You do this 2 to the 2nd power first, then you have the unary operator here, meaning it's -4. So -2 squared is not equal to 4. Okay. If I wanted to make that 4, what do I have to do to this -2 in order to make it a squaring function?
Put it in brackets.
Put it in parentheses. Yes, put it in brackets. Exactly. Yes. Yes. And I cannot stipulate this enough. Parentheses, they're grouping symbols, don't get me wrong, but they're also ways of changing the order of operations, right? You're changing the precedent of the order of operation. So if I wanted to actually take -2 and square that, I would need a parenthetical grouping around it, the brackets around it, right? And by the way, there is a little difference in brackets, right? These types of what's called curve brackets, these are different than what's called angle brackets. These are different than what's called a square bracket. Each one has a little bit different meaning. Now, they could be used interchangeably in some types of math, and also for clarity. For example, if you have like the inner group being this type, right, and then you don't want to have a whole bunch of these, and your next one could be an angle, or not, well, they're called a
Square.
curly bracket. Well, curly bracket, and then the next one will be a square bracket. You can do that for grouping too, but sometimes certain ones have certain meanings. Like you use curly brackets more for sets, right, for elements in a set. I just want to throw that out there.
When you're doing domain and range, they're actually really helpful in trying to show especially when you have a limit to a particular domain range.
Yeah, exactly. So let me ask you, if I had -5 squared here, so this 2 here, I had -5 squared, what is going to be the answer?
It's going to be 25. Negative.
It'd be -25.
It'd be -25.
Oh shit! Yeah, I'm sorry.
That's what I'm saying. You'll lose this negative sign if you're not careful.
Yeah.
So if you have -2 like this written and the 2 squared, you always get this through everybody's head, because I guarantee it. EO, have you not had students mess this up?
Yeah, I mean, we test for this in Calc all the time, and Steve makes a good point. By being as pedantic as we are, we guarantee that a person studying math in Tokyo, a person studying math in South America, a person studying math in Canada, we're all going to arrive at the same answers. And how we guarantee that is by having these rules like order of operations. Go ahead, Steve.
Yeah, exactly. Yeah. The symbols might be a little different. Like in Mexico, they use commas of period. But yeah, the concepts and the symbols are generally the same across the board. But I just want to just beat that in your head. Unless there's a grouping on there, you always do the exponentiation first, and then you attach the unary operator. So well, in like Mexico, instead of having like 10.2, you have 10,2. It means the same thing.
It's not only US.
Yeah, a couple of them symbols do change from place to place.
We use spaces between blocks of thousands, hundreds, millions, etc. But I got to be honest, I miss commas. But in Canada, at least, we use spaces to separate blocks of thousands.
See, I don't like that because I don't think space is supposed to be used as an operator or anything like that. I don't like that, but that's just me. All right, so remember for even then, remember that what we're saying is that -2 squared is not equal to -2 squared. These are not the same things. All this is saying is another way of writing this, right? I'm just putting numbers instead. And so basically for an even function, -x will get you x, and then for an odd function, which is the -3 raised to the 3, I can draw out the negative sign because it's going to be the same amount. It's going to be the same value, right? What if I take a -3 squared, instead of having the 2 here, if I just put a 3 here, what? Let's see here. Actually, I don't want to do it that way because I have to change things around. But I can draw the negative sign out. I get the same answer either way. So it's going to be 3 raised to the 3rd, right? Which is 3 times 3, which is 9 times 3, 18, 27. So this will be -27. Or I can also take -3 and raise to the 3rd, and I still get -27. Either way, I get -27. That doesn't work with these even numbers. That's why this is so critical to memorize. It just happens to work for odd. So you don't have to really memorize that these things that I'm showing you. I just want you to be familiar with it. So moving on.
Steve, hold on, Steve. Subtle point. It's not that it just happens to work. It stems from the fact that -1 to an odd power is -1.
Yeah, like I said initially, right?
+1.
Yeah, because that's what I said initially. -1 times -1 is going to be a positive, and you times it by a negative again, you get -1 again. You keep going over and over and over again. So every time you have an even amount of times you do it, you're going to get positive. You have an odd, you're going to get a negative, right? So if I have negative I, oh, sorry, negative. I have a -1 to the 67th power. Is that negative or positive? Think about it. If I just do it for the 3rd, okay? If I have -1 squared, is that even or odd? Negative times a negative is
-1 squared, so it's going to be positive.
Positive, right? So if I cube it, if I do it one more time,
well,
so I have -1 times
whether you write it with brackets or not.
Well, forget the brackets. Yeah, -1. But so I have a cubic function, and the -1 is negative, right? Right.
-1 squared without the brackets will be -1.
Okay, so if I do that to the 7th power, is it negative?
It's going to be negative since it's odd, isn't it?
If I do it to the 1433 power, is it going to be negative?
It's negative because it's odd.
And we can say that in math. There are actually proofs for this kind of stuff, but once you have a proof where you know that for any negative, or excuse me, odd number, you're going to end up with a negative like that, negative output, you can apply that across the board. But that's for when you do rigorous proofs and stuff like that. But okay, so even functions. I am so wound up right now. I was like sleepy before, but I'm actually getting into this. We have anybody watching? Like 3 people? What do we have watching? 3 people?
10.
Oh, we have 10 people watching.
10 people watching.
Smart people. Awesome. So for any odd functions, if and only f x minus x equals negative f of x, which is just basically saying this up here for all of x in the domain of f. And odd functions produce a symmetry about the origin, which I've already showed you. And I wanted to add that most functions are neither even nor odd. When I gave you the example 3x minus x plus 1, it's neither odd nor even. Can anybody tell me why it's neither odd nor even? Is this by looking at it? Or do you want me to actually graph it for you? All right, let's graph it because I already planned ahead. Here's what that graph looks like. And again, you do a lot of graphing. Can you imagine what it would have been like if we had these technologies when we were like back in nuke school and college? I mean, some of you guys go in college now, but this would have been gold mine shit, man. This would have been with billions of dollars for this program, right?
Well, see,
for
context, Sir Isaac Newton and the giants in the 1600s had to use logarithmic tables to do calculations. Can you imagine what they would have done with calculators?
Oh my God, we would have been on Mars by now. We would have been exploring the galaxy. Seriously, if you guys never had to use a slide ruler, be grateful. All right, so here's what this function looks like. So let's look at it from 2 ways. Is it even, right? What does even mean? It means it's symmetrical with respect to what? You guys forgotten already.
Come on, guys. The y-axis.
The y-axis. This is not symmetrical from the y-axis, so it's not even. Is it odd? Remember what the what is the odd symmetrical for with respect to? The origin. Is this symmetrical with respect to the origin? Say no. Say
no. No.
Yeah,
No.
It needs to look like you guys are paying attention. No, it's not. No, it looks like an odd function, but it's not, because it's with respect to the 1 on the y-axis, not the same thing. Now, if I got rid of all this, let's just magically make it go away. Now, is that an odd function? Say yes.
Hello? Fuck, my mic working. Yes. What is that?
Okay. Yes.
X to the, was it x cubed minus x plus 1?
No, just x to the cube. Is that an odd function?
Yeah, it's a function.
An odd function.
It's not. What? Wait, hold on. No, you changed it because it was x minus. Well,
yeah, no, I get rid of all that.
Oh,
it's a third. Is this symmetrical with respect to the origin?
Yeah, it's symmetrical.
That's then so if it's symmetrical with the origin with respect to the origin, what does that make it? Even or odd? Say odd.
Should make it odd. Odd, is it?
Go with odd. I'm guessing it's odd. Yeah, what do you think?
Is it odd because of the odd number in the because of the
It's odd because it's symmetrical with respect to the origin. 0, 0.
Right. So let me review those two criteria. If x, y is a point on an odd function, minus x minus y is also a point on an odd function. That's what it means to be symmetric with respect to the origin. Also, if you flip this graph over the y-axis and then flip it over the x-axis, you'll get the same graph you started with. That's how you know if it's odd. Steve, I want to point out the sum
this one right here, yeah.
The sum of 2 odd functions is odd, and the sum of 2 even functions is even. And we can leave that as a proof.
That's true. I actually have that. I actually have that in my calc book, believe it or not. But I didn't bother with that. But that's in there. Okay, so a little bit of other trivia before we start going on. And again, there might be some function that in some higher mass that this might not hold true. There was something that I was reading about, but for let's say for basic reasoning, what's the only real function that's both even and odd? And that's the function f of x equals 0. Okay, and the reason for that is if I put f of x equals 0, so here's that function. Let me show you. Here's what that function looks like. F of x equals 0. And you barely can see it, but where do you think this line is at? Can you see it?
Can't see shit.
See the x-axis.
Is it that hard to see? Look at the x-axis.
Is it on top? Oh, it's laying over the x-axis?
It's laying on the x-axis, right?
I don't see shit.
Because think about this. For any value of x that I put in that function, anything, pick a number between 1 and 10, just because that's my scaling thing. Like 4. Okay. So I go boom, boom, boom here to 4. Well, it just says f of x equals 0. So at 4, what's my y?
0.
0. Pick another number.
8.
8. I go over here on my 8-axis. What is the function? F of x equals 0. So what's my y-axis?
0.
0. So I mean, no matter what y I have 0. Does it have symmetry with respect to the y-axis?
It does.
Yeah, I mean, I don't think it
It's
has a choice.
odd and even.
Because everything on this side is symmetrical with that side, so it has respect with the y origin, or excuse me, the y-axis.
Steve, let me help the younger.
Well, hang on one sec. Is this have symmetry with respect to the origin and the y-axis, both of them? Here's the y-axis is 0, right? It also has
both odd and even.
It does. It has symmetry to both the origin and to the y-axis. This function is both even and odd. It's really hard to see. You know what? I guess I can actually change the color here. One sec. Maybe easier to see. There we go. Now, can you guys see it? Is that better?
Yeah.
Okay. So now you can definitely like see that yellow orange thing. It has a symmetry from the origin, which is right here. Everything on this side is symmetrical with this side. It also has a symmetry with respect to the y-axis, because everything on this side of the y-axis is symmetrical to this side. So it is both even and odd. And now you want to say something, Eo?
I was just going to help the younger students in here, and Barney. Imagine this: if you want to see if a function is symmetric with respect to the y-axis, imagine a third dimension. Imagine you turn the function 180 degrees. If you get the same thing you started with, then you know that it's symmetric. Or just imagine flipping, or if you can just see it, flip the graph over the y-axis. If you get the same graph, then you know it's symmetric with respect to the y-axis.
If you take a point and draw a line through the origin of that point, you should find another point on the graph at the exact same distance.
Yes, if you draw a horizontal line from one point and it intersects the graph in the exact same place, the same y-coordinate, then yes. Very good.
Also, let me show you this again real quick, because I wrote it this way for a reason. So what this is saying, f of x minus f minus x equal to 0. Okay, so if this is actually true. If I have a function and I have the function of the inverse x, they're always going to be equal to 0. Okay, they just basically cancel each other out. So in this particular instance, f of x is equal to 0. I just have a straight line, right? So because f of x plus f minus x equals 0, what? Don't say yo. Anybody trying to read this fancy language right here? What do you think this actually means? If you just kind of interpret what you think this means. See the 0 upside down a x, funny looking symbol r. Well, just kind of parse it out. What do you think that's actually saying?
Alpha equals the omega.
Close, but no. What it's saying
is true if x is element of real numbers.
All this is saying. This is called a existential quantifier.
No, universal
quantifier. Why do I always get universals and existentials confused? This is a universal quantifier. So what this is saying for all of x, as x is an element of r. So any element of r where x is a real number, okay? For any value of x, for all of x in that entire set, it doesn't matter what value you pick for x, what do you think the y is going to be?
At 0.
At 0.
We need to broadcast people.
I gave you guys mods. Okay.
So. Okay, broadcasting.
I don't have mods.
I have mods. Okay. So that's what this little fancy universal quantifier and this actually set notation. And by the way, I probably may have a presentation on set builder notation at one time. Do you think that'd be kind of beneficial, or do you think it's not bother?
I think just going over basic domains and ranges and taking some time to show what sets we're talking about and the limits to certain domains and ranges and the rules involved with that would have definitely been helpful.
Okay. So here's the thing. They use these same symbols in logic. So you have what Steve wrote, the universal quantifier, and the opposite of that would be the existential qualifier. So for example, all men are immortal. Well, you could find one who dies, then you'd have the negation of that. That's
and what letter? Logic. What do you anybody want to guess what that letter is? If
the R?
If A means all, right? All of for the universal quantifier. What is the existential quantifier that means? It literally means there exist, but it's a backwards.
It's a backwards Z.
Yeah. Right, I don't even. Do I know? So, I remember how to actually do that in this program. Go ahead.
So, but hold on. This for logic. This is actually really cool, guys. So, for every x, what would the negation of that be? Does everyone understand? You only need one bad guy. There exists something that breaks your rule. And what would the negation of be? There exists something. Well, for every. So they are negations of each other. Does everyone understand that?
You'll see them a lot when you do things for all of x. There exists y such that you'll see it in kind of that format. So, excuse me, for all of x values, you're going to get some kind of y. You'll see these relationships between the universal quantifier and the existential quantifier, but until you start going into higher math, you probably aren't going to really run into them. But I'm trying to expose people little by little with these types of terms because they will eventually see them, and if they're exposed to them now, they go, "Oh yeah, I know what that upside down A means." It's not a complicated thing. It kind of is actually when you start looking at it, but here it's really simple. It just means all of x as element of r. Okay.
What's the proper name of that notation?
That is called a universal quantifier.
No, not of the character, of the notation.
Oh, it's just
I have no idea.
It's just I call them all
like if you want to Google a list of characters used in such notation,
you could look up universal quantifiers and you'll find these.
okay.
Yeah. And then anybody know what that little e symbol is called? Anybody take a guess? It means element, but what, you know? I think it's a form of epsilon, but is that true? Is that where it's derived from, EO? Do you know?
That would be my guess.
I think so.
It looks like the Greek E, but yeah.
Yeah. But that means an element symbol. And do you guys ever take set theory at all? So if I have an element of a set, like if I set my set is 1, 2, 3, what are the elements of that set?
1, 2, and 3.
1, 2, and 3. I have 3 elements, right? Okay, so we'll have to hang out on that kind of stuff. You know what's funny, EO? You don't realize how much math you have to learn until you're actually doing it, right? It's like, holy shit, one thing leads to another, leads to another thing, leads to another. It's ridiculous, isn't it?
Wait, you know, it's funny because if you go back in the history of science, they had the plum pudding model of the atom, etc. So
yeah, sure.
Mathematicians used to be proud of the saying, for every generation, one generation tears down what the previous generation built. But mathematics alone, you know, we're using the same math that the Greeks used, etc. We've just built a higher and higher skyscraper. Now, having said that, with the advent of the scientific method and the peer review process, it's no longer true that we tear down everything. We add and augment in science. I just don't want...
Yeah, you try to, right? But except for the plum pudding model as well.
But that was a long time ago. I don't want any young Earth creationists doing sound bites.
Yeah.
What I just said.
No.
God.
By the way, yeah, I don't subscribe to the plum pudding model in physics, people. Okay, I don't even subscribe to the Bohr model. So whatever.
The Copenhagen interpretation.
Well, that's the wave functions. Bohr model is basically relationships to the electrons of the nuclei. But anyways, nucleus. So moving on.
Yeah, right.
Let's find the function of f of x defined by the composite function given by functions f. Here we're going to do some problems, okay, everybody? And Renee is in the audience. She's learning math. She's making her eyes twitch, but she's learning math. For a girl, that's pretty good. You know, for a girl learning math, Renee, props to you. I'm glad you're not making a sandwich. No, it's an inside joke.
He's talking about an age, like girl, like like very young, not
no.
Young.
Did you guys miss it? Did you guys miss it the other day? It was freaking hilarious.
This is patriarchy.
Yeah.
Misogyny.
She had posted this amazing post from MK. That was the most.
Oh my God.
You saw? I know, because Jay knows what. You read it. Was that the most misogynistic fuckery of all time?
Pretty much.
I was rolling, and Renee did the most brilliant thing she could. She just took it in stride and just ran with it. And I was like, "That's awesome. That was awesome." It was so condescending. Oh,
I didn't get it.
That kind of comment is pretty special because most chicks don't leave comments like that.
Women aren't deep thinkers, you know.
That's what he was basically implying. Yeah. They don't usually think about this stuff because they don't think about anything. Anyways, we're off topic.
Yeah, I know.
It's definitely in my inside joke with Renee. Renee gets it. But I got to tell you, she does make good sandwiches, though. So
yeah,
props to her.
Oh yeah, you mean like that? Never mind. You saw that picture.
Was really. If we ever did run into Renee, she'd probably kill me. But she's overseas now. She moved over with her husband in Europe, I think, didn't she? Boyfriend or whatever. So yeah, I would have got a kick out of that too, Renee. All right, so moving on. So let's try figuring out what we're going to do here. We're actually going to do the opposite rather than the decomposition. We're going to actually put them together. So if I give you, right, y equals u cubed and u equals x squared, I just substitute the second equation into the first, right? So what do you think this is going to look like? I'm going to take x squared and I'm going to stick this where u is, right? So I end up with y, right? I'm with the cube of x squared. Now, don't forget this. When you have an exponent, right? It's called the power rule for exponents, and I just specifically added in here so people don't forget. A to the m raised to the n, you just times them together, the product. Okay, it's the product of m times n. So x squared raised to the third power is 3 times 2, which gives me x to the 6th. We haven't gone over an exponent, so I kind of threw this in there. Hopefully people might remember that. But do you guys know about exponents of how to do those? So if I have x squared,
I'm glad you reminded me because I did completely forget about that rule.
Yeah, remember the power rule for exponents is a to the m, and then you raise the next exponent. You times them together. You do the product. But if you're just adding them, right? What is x squared plus x cubed? What do I get?
No, it would be x squared times x cubed.
No. If I just have x squared plus if I just have x squared plus
what's
x cubed.
I can't remember what it's called. You would actually say like x squared plus x cubed. Like you would separate them. What's that?
Well, hang on. What is x cubed? What is x cubed plus x squared, or x squared plus x cubed? It's common to commutative. So take x squared, right, and I add x cubed to it.
You didn't want to say add there, Steve, but you have to be careful. So
yeah, no, I'm sorry. I'm not. God damn it.
Yeah, multiply.
You can't add those together, obviously.
So everyone, whenever you raise an exponential expression to another power, you go ahead.
Well, you can't, but you can.
Oh,
okay,
break it up.
Okay. Here's where it gets in screw, because if you do, when you're trying to factor stuff, right, you can't really take x squared plus x cubed, but you can put them together and you can draw out an x cubed from it, right? And if I take x cubed, I'm doing in my head. If I take x cubed out of that, right, I end up with x cubed 1 plus x.
No, if you take x squared out.
X squared. Yeah, that's right. You factor x squared.
X squared out. You've got parentheses. Okay, x squared times
parentheses x plus 1.
Parentheses 1 plus x. Close parentheses.
1 plus x.
Yeah.
Or x plus 1. It doesn't matter.
Keep track of what
either way.
you're doing it verbally.
Yeah. Well, it's weird, because when you're actually doing these problems, sometimes when I used to be able to do them back in the day, you just kind of remember this stuff, right? But let's say, okay, who's in here, by the way? Let's see here. Let me ask somebody. Kaiser cube. If this is just a little bit of a review here. If I have 2x squared, okay, 2x squared, and I add another 2x squared to that, can I do that? Can I get something out of it? What is 2x squared plus 2x squared? Do you know?
Oh God, you're killing me.
Let me tell you how to solve this.
Oh no. Well, I wanted to guess. I wanted to see if I can guess. I know I'm gonna make a total idiot of myself, but I want to try out. Well, with the 2 part, with the 2x, I would probably the 2.
You're breaking up. Did he break up?
Yep.
Okay.
Yeah.
Yeah. I can't. Kaiser, you broke up.
Oh shoot! Sorry.
Try again, and then I'll help you with it if you get it wrong. So 2x squared plus 2x squared is what?
Would it?
Yeah, let me just help you with this.
All right.
2 apples plus 2 apples equals how many apples?
4.
I was going to say that exactly.
Okay, there you go.
So would it be 4x to the 4th?
Yeah. No. X squared is just like an apple. Think of it as a unit.
Right.
Okay. So 2x squared plus 2x squared
is
equal to
4x squared. Okay.
Right. I'm telling you guys now, if you think of these things as just a unit, you'll be golden.
Well, I knew that the correlation, I knew that could be added, but I wasn't sure about the squared part.
Let me give you another one. If I have 2x cubed plus 2x cubed, what is that?
That'd be 4x cubed.
There you go. X cubed is just like an apple. Perfect. Okay, so we're on the same page here.
So, Steve, let me take Jay's point. Whenever you multiply exponential expressions with like bases, yes, you add the exponents. But here we have a situation where we have an exponential expression raised to a power itself, and then we have to multiply exponents. But, Steve, I think...
Yeah, those are only the like bases. X squared and x squared are like. So that's why I can take 2x squared and add it to x squared. And all I'm doing is I'm adding the coefficients together and saying, how many x squares do I have? Well, I had 2x squares. Now I've got 4x squares. That's it.
So what if you would have? What if you'd have 2x squared with 2x cubed, something like that?
Well, again, if you have x squared plus x cubed, they're different. They're different things.
Oranges,
right? Apples and oranges. But what you could do when you're factoring, right? If you think about it in your head, picture this in your head: x squared plus x cubed. If I take x squared out of what I have, right? What is left over in the first place? I'm left with 1, right? Because x squared times 1 is 1. Plus,
right.
I take an x squared out of an x cubed. I have 1x left. So I have x squared, parentheses, 1 plus x. Or you can say x squared, parentheses, x plus 1. That's how you factor. Those are some tricks you have to do when you try to simplify things, right? Because I'll tell you, the hardest part in math The hardest part for me in math was learning the tricks to simplify something to where I can continue on and do the proof or something.
Yeah.
Right. For example,
the hardest part is selecting which process to use to
right.
Yeah.
Like,
go ahead, Jane.
I was going to say, the reason you might do something like that is if you had an x squared in the denominator.
You want to cancel. Yeah, exactly.
Right. So then you'd cancel x squared. And that's why you would simplify something like x squared plus x cubed to x times parentheses 1 plus x.
That's a brilliant reason why you would do that. You would draw out the x squared, because if you have an x squared in the denominator, and you can cancel. And remember, again, be very careful when you're canceling. You cannot cancel across multiplication and subtraction unless you have the same base. And that's why when I showed you when we're doing limits, I actually broke it into individual bases to show you this is how you can actually do it this
Denominators.
way. Denominators have to be the same.
Shit.
Yeah.
Do you have any idea how many times I've made that mistake?
Oh,
Holy
yeah.
shit.
No, it's a common mistake. It's a very common mistake.
So, Steve, I've got to take off. I just want to say that
we're not even close to being done here, dude. No, we're about done with this one. But I got power rule and chain rule, but I don't think I'm gonna do that.
You're in good hands with Jade. I just want to say.
Oh yeah, Jade knows what the fuck she's doing.
Kaiser Cube. It's really important. Anyone who's watching, it's really important to learn the exponential laws because it comes up all the time in higher math. And so, sorry, just one little thing. To learn the charge of a neutron or a proton, all you need is grade 5 math with fractions, up quark and down quark. Steve can tell you about that, but math is infinitely useful. For example, the Schrodinger wave uses vector spaces. It's just math pops up everywhere, everyone. Anyway, take care.
Thanks, man. Well,
I guess you figure that I'm not going to
the main. I actually. Sorry,
it's up, down. By the way, for a proton, it's up, down for a neutron. But go ahead.
One thing I use math a lot, especially functions a lot, and I really just did it, not really thinking about it, was writing code. What I would do a lot of PHP code, and this stuff is incredibly important to me.
Oh yeah, coding, you have to know math, man. By the way, we lost Drag. He didn't even say he left.
Yeah, no, he said he had to put the kid to bed. Okay. Steve, did you go over at some point all the basic, the rules for math, like the associative, commutative?
No, we didn't start that basic. We've been skipping around. The way I've been doing this is because I went to different levels because I didn't want to start from the very beginning because there's people much higher, and so I've been kind of going, okay, like one of the first ones I did was Calc 2, almost Calc 3, which was the Taylor series.
Yeah, I know that.
That was a high level thing. You can't just start off with that and expect to be able to do that. But there was people that are at that level, and they're like, yeah, I've had this before. That was more of a review, right?
Right.
So.
Well, I was just thinking at some point we should do basic algebra, for those people who aren't at this level. And I mean, I could do that if you want.
Yeah, do it. No, seriously. Yeah, if you were a manager, so you just run with it. Do a presentation. Let's get people involved.
I'll do that and start with the basic rules of math. Because when you start with the law of identity, the laws of inverse, the commutative, associative, distributive, and you look at those things, and you also get people to realize that there's really only one thing, and it's addition. Everything else is a variation of addition.
It's addition and multiplication, and rings.
Well, no, multiplication is just
multiplication
addition.
is addition.
Nope.
Right.
Nope.
Yes,
No. In multiplication,
yes, it is.
In ring theory.
Okay, what is 2 times? No, we're talking about basic algebra.
Okay, but I'm talking in higher math.
Yes, but if you're going to start teaching people basic algebra, you just teach them basic algebra. Yeah. Okay, it's just like teaching science. You know how some of the fundies will complain, well, they didn't teach me that. Well, that's because we teach you the beginning, and then when you get a little bit more complicated, then we teach you there's more to it.
Yeah, I mean, because when you start getting anything like Abelian groups, and you start getting into okay, you have the condition for multiplication.
Right. Yes. Yeah.
And what's some of the other ones? It holds for distribution and multiplication over addition. It holds for commutativity. I mean, I remember those things, but yeah.
But yeah, you
quadratic equations.
Yes, we
drags during quadratic.
Yes, quadratic. I love quadratic equations. We start with the very basics. And you tell people, okay, I'm going to give you the basics. There's more to it. It's a little bit like you tell people you can't find the square root of a negative number.
Sure can.
Well, not in the beginning. You can't. You tell them You know, you can't find right now with what you know right now. You can't find the square root of a negative number. That's for later.
Okay.
You get people to understand how to do the basic manipulations. I mean, you tell people, you know, we're dealing with adults, not children, so you can tell people, okay, there's going to be more to this when we go on, but right now we're just dealing with the basics. And so you show them that, you know, really when we're starting at the basics, we really just have addition, because 3 times 2 is just adding together 3 2s.
Yeah, it's hard with words out. You just want to do the field axioms.
Right. So that's what I'm talking about. Talking about the very basics.
You want to get maybe the Pino's axioms as well. And maybe
you can do absolutely anything you want. You can even pick your own axioms and try to derive your own math.
Well, if you're a mathematical constructionist, that's what they do.
Right.
But it's still math.
Right.
You just have to be very careful how you define the axioms and that it's internally consistent.
Running out of time here. So
yeah, let's keep going. Yeah.
All right. So here we have a situation where we have 3 different functions, right? So all you do is just stick one to the other one. So my first function is x cubed. I stick that over to here where the v is. So I end up with 1 plus 2 times x cubed, which is right here, the very first thing. I take that whole thing u and I stick it in here. So I end up with the square root of that. So I end up with the square root of 1 plus 2 times x cubed, which is basically saying this, square root of 1 plus 2x cubed. That's it. That's all you do. That's easy. So here we're going to break it down. We're going to do the opposite. So x equals 1 plus x squared cubed as a output that goes to the squaring function, right? So I could write this down with the middle function, 1 plus x cubed is equal to u, and then to say y is equal to u squared. Again, you'll be doing a lot of this in calculus, a lot, because you're always breaking it down to this form, so you can work with the product rule and the chain rule, which we'll do next time. So here's a good one right here. Y equals 1 over 1 plus x to the cube. What is going to be my u value? What do I want to assign to u?
1 plus x cubed.
1 plus x cubed. Okay, and so y is going to be equal to what? 1 over
u.
1 over u. And I can also write y equals 1 over u, or I can say y equals u raised to the negative 1, right?
That's the way I do it.
And I wanted people exposed to negative fractions for this very reason. Negative fraction just means it is u underneath the horizontal bar, or some people will call that particular one called a maniculum. This is actually a solidus. This is actually a slash, they call it. It means division. But when it's like this horizontal bar, that is a maniculum, and this negative sign means that this means to be under that, okay? And then you're just saying u equals 1 plus x cubed. So basically, yeah, this is exactly how you did that. And that's it. That's composite functions.
Yeah, the negative exponents become really important when you start dealing with a lot of exponents.
Yeah, and then you start getting into like fractional. Like, for example, if I say x raised to the 2/3, people freak out. It's like, look, all that means is you're taking the cube root of x squared.
Right, exactly. But if you have something like, we've already talked about powers. So what if you have something like x to the negative 1 squared? The x to the negative 1, and then you're squaring that whole thing.
Well, that would just be x.
Yeah, but the thing is it's easier to deal with negative exponents when you've got a whole bunch of stuff together, and you're either adding them. If you're multiplying like x to the negative 1 times x cubed.
Well, I mean, I think when you do your,
and then you've got x to the negative 3, because when you're multiplying values with exponents, if the same value like x, you then add the exponents together. I mean, not x negative 3. You then add the exponents together. So x to the negative 1 times x to the negative 3 would be x to the negative 2. X to the 2.
And also,
damn, I'm tripping over my tongue here, but you know what I mean.
I haven't done, I know what you mean, but I haven't done one for the quotients yet. But if I have like x cubed divided by x squared, can anybody do that in their head? It's not that hard, but
yeah, but it's also the same thing as x cubed times x to the negative 2.
Yeah, and well, that's how you have to think about it. You have to think about the negative in terms of negative exponents, right? But but in your head though, if you're looking at it in your head, you say x, yeah, but could you give a reason why though? Think about this. If I have x cubed over x x squared, right?
Right.
What I'm basically doing is I'm saying, okay, I can take away 2 x's from the top and 2 x's from the bottom. I'm left with one x at the bottom and excuse me, one x at the top over 1.
This is basically 1 over 0, right? It would be the same as 1.
It's x over 1.
No.
Right?
Wait, you can't do that. What did I just say? Holy crap!
Did 1 over 0. Think
But
about
another way to look at that, if you said you had, x cubed over x squared, was that the way you did it? X cubed over
x cubed over x squared leaves you 1 x on top and 1 on the bottom, leaving you x over 1, which is x.
Right, but I was going to say another way to look at that, if you wanted to, separate it out, it'd be x times x squared on the top and x squared on the bottom, and then the 2x squared cancels out, leaving you with an x.
Yeah, you can do it that way, and there's a few different ways that could be done.
Oh yeah, yeah.
I do I used to do like the railroad track methods for like stoichiometric chemistry, but when we were working with like factorials like this, it's not factorial, sorry, when we're working with fractions like that, I just find it easier because I can look at a fraction, or back then I could, I'd probably have to review it, but I can say, okay, I know what cancels with what here. I know this is in the denominator here. I can cancel with the new over here, and I can cancel things out easier that way, because when you start dealing with fractional notations, it's kind of a little more difficult to cancel. But if I just say x cubed over x squared, okay, well, I just take away an x cubed from the bottom. Right. I left with 1. I take away a x squared from the top. I left with x over 1. So.
Right. Well,
okay,
I was just going to say, in my experience in tutoring, for some people, you have to be very visual.
So I should be doing this naked?
What?
I should be doing this naked?
Yes, that too. But what I mean is you have to show every step. So to take the x out and go x times x squared on the top and then x squared on the bottom is more visual for them.
Yeah, and I wish I had the ability to show that. I need to find a way, and I've had people offer to get me one, but I don't know which one would work. I need to find a writing pen that will work with OpenOffice Math the way I could just cancel things out. And I don't know if any of them work that way. I have no idea.
Yeah, I don't know. I got a stylus for my iPad, and I haven't tried working with it yet, but I'm going to. I also have a couple of math writing programs on the iPad, but it's so much easier. I also do have a whatchamacallit here, a tablet, the kind you can write on, but I don't know how good it is, but yeah, because it's so much easier to pick up a pen and just to do it. Write things out. Yeah.
Yeah, but also just get a webcam and a piece of paper and point the webcam at the piece of paper.
No, I want to be able to do it. I want to actually write it.
That's kind of awkward, I think. Yeah. Yeah, you're right, though. I thought about doing that. Yeah, you're right. But it's also easier to erase stuff or correct it when you're using a tablet or online or something.
Of course.
Yeah, but yeah.
Okay, do you guys want to see what we're working on next time? If I can actually have to work.
Let's see. What are you doing?
Okay. We are doing blah, blah, blah.
Steve,
boom! Oh, hell of a lot more complicated shit. Just go through it real quick. What do you guys think? That's what we're working on next time.
Let's see.
I'm not seeing the screen share.
Oh, I guess I got a screen share. Okay, you guys prepared for this?
Mm-hmm.
Okay, this is higher level calc here, but we're gonna jump right into it. Present. Okay, so this is the product constraint rule, and I'm not gonna do it right now, but this is all the different notations. I'm gonna show you all the different ways of doing it. I'm showing you how to do first principles as I'm taking from Wikipedia and explaining, because Wikipedia doesn't explain what the shit this thing. This is, and by the way, this is what I mean. Wikipedia is fine for like quick information, but if you don't know what it's saying, you don't have a background in it, you won't get it, right? Yeah. Because so when I look at the proof there, I actually knew how to read it, and I actually was breaking it down. I wanted to show what it is, and I'll explain it. But then I'm going through all this, and I'm going to be showing this kind of stuff, and we're going to get into like special cases, like for constants and differentiation, and yeah, it's going to be the chain rule, right? And why we had to use complex functions, right? So yeah. Decompositions function. We're going to be, so it's a little more technical, right? A little more in depth. Mm-hmm. So it's not going to be, it's not going to be light stuff. But that's the meat of potatoes.
Looks like I'm going to have to take a couple of make a couple of visits to Khan Academy before that happens.
I can tell you right now, the 3 most important things in calculus, as far as like the things to remember, are the product rule, the chain rule, and the quotient rule. And then for integration, it would probably be the fundamental theorems fundamental theorems of calculus, right? Which you don't have to know at this moment, but it's just basically like, for example, if I want to take integral of two different functions, you can do it across the indices for like 0 to a and a to b and whatever.
For a second there, I thought you were trying to say the Thunderfoot theories.
No, it's just a way to do integration. But for the chain rule is the most critical rule, I think, probably in calculus, because if you screw that up at the beginning and don't conceptually understand what's going on, you'll be lost forever in a day.
You know what I think might be a good idea too, now that you're doing this,
yeah,
is to do a post, or let's have a place where people can ask questions. You know, and I mean, just, you know, if you have any questions, just ask them, because I know people will be watching this at different times. And so, and not even just under each video, but just any place. Just have a place where you can ask any math questions, and, you know, people will try to help, you know, if they don't understand something here. I'm sure there are probably people out there who are still confused about what a function is. That was one thing that drove me crazy in tutoring.
Yeah, I don't have a good idea to answer quick Q&A though. That's why I have EO. Yeah. Again, I'm reviewing this stuff piecemeal, right?
Yeah.
But Jay, let me ask you, because you've had Calc before. This is what I think is funny when I see these people on the like the Conqueror Posse that have no knowledge of any of this stuff, right? They've never bothered learning any of this stuff. It's not something you just pick up, right? I mean, I could not have learned this stuff in the last couple of days. Obviously, I've had it before, and this is a review for me. And I'm really actually enjoying explaining it. I really actually am. But I mean, can they really look at somebody like myself who, yeah, I'm not Sam, I'm not Fiona, right? I'm not even you. But you know what? I'm not an idiot either. I've had this stuff. So can you tell that I at least had some mathematical training?
Oh, yeah, sure. And I think it's hilarious when they say that you have no content on your channel and that other people have no content on their channels. It's clear they don't look at those channels.
Well, they've never see. I always mock stuff. They never listen to my technical stuff, right? When I made my videos, they have no idea what my knowledge level was. They have no idea what my education was. They don't know. And even though it's not on par with a lot of people in the community, it's still bachelor's level shit. I mean, I got over 120 credits. It's like you know, you didn't finish your degree, but we had to learn a lot of crap, right?
God. As I mentioned before, I've had astronomy 3 times.
Oh, I took astronomy in the lab.
Well, the reason I had astronomy 3 times.
No, I only took it once. It was an easy class, but it was boring because I remember it pretty vividly. We had to learn about like the Terminator line, the celestial sphere, and I was like, well, I already knew all this shit.
I took it 3 times because over about a period of about 15 years, because it kept changing during that time period.
That might be true too. Rob says, I think you made an extremely important point when you say this is something that a layperson can learn and they take interest in. Yeah, I'm a layperson. I had maths. I went through Naval Nuclear Power School. I was a supervisor for 2 types of reactor core systems. I had to learn, you know, pretty decent level of physics and math, even though I can't do any of the physics anymore. But I am a layperson. But I can show anybody that a layperson can do this. You can do it.
Well, see, speaking of lay people, like, look, when this is actually before I got really serious with that, I actually got into coding far before I got serious with math. And I'll tell you an example. I had to make a function, a code of function. Let me see if I can explain this right. I have a bad bandwidth, I know. I had to make a code in which I can't explain it now.
That's okay. We got to close it up anyway. So next time,
Do you think there'd be interest or need in the Great Debate community to have a coding session or a coding course?
Oh, I think that'd be great.
Probably, but yeah, I wouldn't. I mean, I used to program in Visual Basic. I wrote a database program for my Radio Shack store to track special parts. I wrote it in VB based upon a program, a database that I had programmed in college computers. And the program that I wrote, the instructor actually used for his advanced class because I was only supposed to write this very simple database, sequential database, and I actually wrote what's called what I call a Rolodex program. I had the graphics that looked like a Rolodex card. This was all back in the should be early 90s, right? Wasn't like we had modern shit. And I wrote this really good database where you can put in the field, put your name, last name, address, and all this other stuff. And then I just ported it over to Visual Basic because the coding was pretty much similar. It's just the GUI for the Visual Basic. You add like the forms, right? But I don't remember how to do that stuff. But I was pretty good at one time. But I got to tell you, Midnight. Hang on one second, we got to get going. Midnight said, you know, you can learn this stuff on your own if you have the free will to do so, and I think you can learn most of it. But this is the problem that you run into. If you haven't had any kind of formal mathematics and you're thinking like the clown car posse that all of a sudden you know more than people that actually have had formal education, you're going to be severely deluding yourself. And this is the reasons why. Because even how many mistakes I made, you know, EO has to point them out, which is great. But if you don't know the foundations, you're going to get lost somewhere down the line. Would you agree, Jade?
Well, I agree. I wanted to say real quick though, because I got brain a lot. What I was making a news group page where like news was reported daily, and it went into a series of rows and columns where you'd have 3 across and say 6 down per page, and as they progressed, you'd have more and more links. You'd have a second link, a third link as you had more and more, and you had to archive history. Well, there was a problem that presented itself with the rows and columns because let's say you at the end, let's say you had a multiple of you have to have multiples of 3, and if you didn't have a multiple of 3, let's say it was 1 or 2, the call span would not come out correctly. You had to make it to where at the end of the list, it would make the call spans be correct in the HTML or would not come out correctly. That was actually more difficult than...
Yeah, well, I mean, even the math program I'm using, you have to make the alignments right. And you have to make... I mean, when you're doing an array, like you're doing a dimensionalization of an array, you have your rows and columns. But by the way, we will be doing matrix at some point. I will be doing a presentation on matrix. But I got to end this because Thaddeus is coming in. This is some kind of theological mumbo-jumbo stuff. Yeah. But anyways, thanks for everybody for watching. If you got questions or if you got... topics you want to discuss that we could probably help out, let me know. Again, don't ask me to do your homework. I suck at solving math problems. That's not my thing. I just can explain things. That's it. So Jade and Kaiser and Barney, thanks for like sticking with us. Renee said that was fun and terrifying. That's the way I like it. Fun and terrifying.
There we go.
Good night.